for not speaking in Spanish tonight, but I think it would be better for you if I just speak English, because if I try to speak Spanish, it's not going to work. And so let's go straight to our point. So this is the topic we are going to explore tonight. Here's tonight. I don't know from this day where you are now, but we're going to talk about the rheology of mine tailings deposits for dambreak analysis. So this will be the contents, the table of contents of your presentation. We're going to have a short introduction. And then after that, we're going to explore the deposit history. And then we're going to move to of course, to talk about muddy flow. And then when you talk about muddy flow, you have to relate to a science called rheology. And then we're going to present to you a case study. And this case study, we are supposed to show you rheological results and numerical simulations. I apologize for not, maybe I'm going to skip the rheological results, because I did a test of this presentation. It took 2 hours. And then I'm going to be a little bit fast. And unfortunately, I'm going to skip this part of rheological results. And then we're going to move to the conclusions. So find tailings discharge consistency. I think many of you have seen this picture before, where it shows several possibilities as far as the tailings consistencies. So in the left, you have the thickened and thickened tailings. So it's very diluted suspension, mineral suspension. And then you have the something a little bit more thick, more cohesive spill. You have the thickened tailings. And then you have something that looks like a paste. And then you have the thickened high density tailings, and then the paste. And also you have the possibility of something that is going to be filtered, and then you have something that resembles a cake. So these are the consistencies that we have, possibilities that we have of this material. Sorry. Oh my gosh. I lost my... Let's start again. Oops. Sorry for this small problem. Talk about the tailings discharge. So this is a scheme where we show two extreme possibilities as far as those consistencies of the tailings. The first one, material is more like a liquid, and then when you pour this material on a flat surface, what is going to see is going to see that material is going to cover, to spill away, cover all the area. If it's a level terrain, it's going to cover all the area. There will be no thickness on this. Of course, if you want to consider a practical thing of pouring a material like this in a proper that has its limits, you may need an structure to hold this material in a particular place. And this structure we call dam or a dike. So you need this in order to have this material in this place. If you go to another extreme of this consistency of these tailings, you're going to see something that is It looks like a solid material, although it's particle material, but it's still a solid material, like a dry sand. When you pour this material, you're going to see a very familiar face, form. It's a cone, and the area that's going to be covered by this spilling is something that you can predict if you know the angle of repose of this. So this is something that we may have for our tailings in the near future. If you move from this conventional tailings disposal to this alternative mode of tailings disposal. Then we can have more material on this same place if you consider this structure. This can be raised a little bit, and then you can have more material like this in the same room. And then we can raise the questions. Is it a den, or is it just a retaining wall? So this is a very important question. If you consider this a den or a retaining wall. In order to answer this question, we will see what's the function of this. What is going to happen if this structure would fail? The answer for that would be something like this. Probably if that thing was going to fail, what is going to have a different, it's going to have a settlement here. And probably this material is going to run to take this place, only that. So in this case, I'm going to say that this material and that structure is working for this material as a retaining wall, not as a dam. If you do the same with this material, what is going to happen? You know, if this material behaves like this material is going to spill away. So in that case, you can say that in this material, if something happens to this retaining structure, this material is going to deform. Maybe experience a large deformation, but it's not going to flow. This material here is going to flow. So it's something completely different as far as the discussion regarding is going to deform or is going to flow. So if you're moving our material, the way we discharge the tailings in this direction, probably what we are going to talk is about a dike or a retaining wall, just to make things a little bit better as far as the quantity that we can hold on this portion here. So for me, it's very important to, if you were going to discuss flow or the large deformation, but without flowing, is that if just me control the time here. We have to discuss more about the deposit history or the fabric of this deposit. So this is another picture that is is known by many of you that work with tailings or in mining. It shows several layers, at least 3 layers, 1, 2, 3, and at different stages. This one's probably is more consistent. It's a material that must be dried for a while. This another one is maybe another one that is being around for a while, but it still shows some movements maybe. And this one is fresh material that was placed on top of this all 3 materials. But what you can say, this one that is here, one day it will be like this as well. So we can say that these materials you have an evolution as far as the condition, its condition. So you can pursue this kind of evolution. We call sometimes aging. Material is transforming. If you consider phenomena that will explain this evolution, talk about the alternative methods. You can see two categories for when you talk about this. The first one is the one that when you have dewatering in the plant, and then when you have dewatering in the plant, no dewatering in the plant, and then you can still discharge this material as a diluted pulp, but in the field, in the disposal area, we're going to see something different from the conventional disposal. We call this subaerial disposition, when you don't do anything with the tailings root in the plant. But sometimes in the plant, what we're going to do is to dewater the tailings before we discharge. And then you're going to see some of these possibilities. One will be the thickened tailings, and then you have the thickened tailings disposal. If you have something a little bit more concentrate, you're going to have a pasta. Sometimes in this pasta, we add additives to make things much better as far as the evolution. And then you also have this possibility of a filtered tailings. And then you have, depending of the amount of filtering that you've done, you can have something that looks like a cake, a dry material, almost dry material. What are the common features of this? All these alternative methods that is going to be the near future, at least in my country. Discontinuous discharging. So you may have something different here because you may require multiple discharging areas or at least sectors because plant doesn't stop. You're going to send tailings to the disposal area all the time. So you may need to dispose sometimes in different places because one of these features is that you have to have its continuous discharging. Another thing is important. You have to work with thin layers. So I'm talking about maybe 30 centimeters, 40 centimeters, no more than that. So otherwise, this thing is not going to work properly. Again, I come back to that same picture. Now I'm just focusing on the names of these different disposal methods. The first one is the conventional, the one that we know very well, the unthickened tailings or thickened tailings, but not that much. And then you have the thickened tailings and thickened and paste tailings. And of course, you have the filtered tailings. So these are the new agenda that we have and with the people that work with tailings discharge. When you talk about these new methods or alternative methods, because these methods are there for a while, for reasons of economics, maybe we just stick to the conventional tailings discharge, but we're going to move now a different scenario as far as the tailings discharge. When you talk about subaerial disposition, because you are discarding material without any dewatering, the material is going to experience a sedimentation once it is in the reservoir. After that, it's going to have a self-weight consolidation. And if you remove the water on top of this material, and then you have chance for a desiccation. So these three phenomena is going to happen in the subaerial and also in the other alternative methods. You see, with secant tailings, even with the paste, we're going to see after disposition, there will be water draining or liquid draining from this paste of this secant tailings. This water that is draining is self-weight consolidation. After that, we're going to have desiccation, okay? So it's very important to understand these issues or these phenomena in order to really have understand how your operation is going to happen. In the past, you used to, we did some work on this, try to model these alternative methods. And the numerical modeling was very simple. We have like a stage of filling and then a stage of resting. During the filling stage, we have consolidation. And even when we stop filling, the consolidation continues. And after we have removed the water, we see we have a chance for desiccation. So the material desiccates for a while, and then comes the new layer or a new cycle of filling and resting. You can repeat this many times, and then you have the model, you can model this correctly, this new or alternative methods. So it's something that there is a rationale on top of it's available for anyone that is going to venture on this new discharging method. Here we can show you some results in the past. We built an area, a test area, a field test, where we filled this with tailings, a dilute tailings with solids content around 20%. So the material sedimentate, and then we let the material consolidate. And then after that, we allow the material we did the surface drainage. So in order to allow the material to desiccate. So here's later in this process with the desiccation happening. So when you model desiccation, you have in the first stage one-dimensional shrinkage, and then after a while you have chance to open cracks, and then this cracks is going to take the model of a three-dimensional stage. So everything can be modeled without any problem. It's interesting when you look this skate area, and you see what's going on under this skin, because it's more like you have more like a crust on top of it, and you are wondering what's going on with the material under the surface. And sometimes you have a big surprise. You see the material do not desiccate because maybe this crust creates a barrier in order to have this exchange between the water that is here and the liquids that are in the material, and the air is on top of it. So this exchange between atmosphere and soil maybe is buried by this crust. You can discuss this, you can work on this. Sometimes what they do is just to rip this crust in order to allow the desiccation penetrates the soil. Another student has done a small scale field test. This is very interesting stuff to, let me just move this if I can. Oh, yeah. And then in this picture, or in this experiment, what he did is just make a very small pond. This pond has like 40 centimeters or something like this, thick. And then what he did, he sampled this from time to time. He also has done some undrained shear strain measurement and also measure suction. So let me talk about the whole story here. Until the day 45, the material was just discharged on that area, allowed to sedimentate and then consolidate. At the year 45, the material was just consolidate when he did this sampling. Okay, so you see high void ratios. It's the same material. The things that I'm going to show you guys is the same material. That's really nice stuff because we just have done several works on this material in different times in the past. So this was at the end of the consolidation. And then at day 86, or like 40 days after that, we came back again to the area and also did the sampling. And then the material was with this void ratio profile. And then we kept them doing this during several days until what we observed that as desiccation was coming on, was happening, of course, the material started to desiccate. In this case, because it was a thin layer, the desiccation could progress all over the thickness of this material. So that was very interesting stuff. As I said, we also measured undrained shear strain with a vane. And the first measurement happened in day 86, and then we got something like this, very small numbers for undrained shear strain. And then after material starts to desiccate, what happened? We got higher and higher undrained shear strength. So this is really interesting. And that's thing what may happen if you do the right thing as far as the alternative methods. So that's something that I'd like to share with you before we move. Another thing is interesting about this desiccation thing, allowing desiccation to happen. This is another test done by the same student. He supposed a conventional disposal. He made the modeling now for something in the real scale in the field, something that has like 70 meters at the end of the filling stage. This is the void ratio profile at the end of the filling stage. And then it allowed desiccate the material. When they allowed desiccate, what happened to the profiles were more like this. And on the other side, using the same numbers that we have for that small scale relating suction, for example, with the undrained shear strain, we could model how was going to transform or increase or evolve the undrained shear strength. And of course, the desiccation starts on top of the layer and starts going down until we reach maybe something in the middle of this field. And of course, the desiccation, because it was a thick layer, wasn't that much effective. But at least you see the beginning of the near surface material was really in a condition much better that what would have if your material was just consolidated. This would be the undrained shear strain if the material was just consolidated. So what he has done later, he has did this exercise of building or try to construct an access road on top of these tailings in 2 years. In 2 years, at year 8, it means year 8 means the end of the consolidation or the end of the filling and the waiting for the consolidation, and the year 9, that is this undrained shear strain profile. Look what he got as far as the stability analysis. In this case, for this height of fill on top of this material that was just consolidated, he got something that below 1. So the factor of safety was below 1. So this fill wouldn't be there because the factor of safety is less than 1. When he considered to do the same work at the year 9.9 or 2 years later, allowing the desiccation to happen, the factor of safety was 1.562. So much better scenario as far as risk. So in this case, it'll be okay. And then we can have like maybe a field that will be a little bit higher or taller. So this introduction or this background is important for me because we are going to discuss the possibility the material deform, slide, or flow. And the material is not water. The material comes from the alternative methods. So in this case, we have to discuss a little bit of this rheology of this deposit. So that's why I did that introduction, that theoretical framework. But of course, let's stick to our plan, talk about dambreak. And then we're going to talk about mud flow. It's not water flow, it's mud flow. It's something that, if you remember, Brumadinho, Fundão, you see the materials flowing. So that's things that are in people's mind. And so that's why it's so difficult now to convince people that what we are talking here is fine tailings. It's not a non-cohesive. We are not talking about liquefaction or not about soft clay. Like we're trying to talk about a material that maybe desiccates. Material that is now, if it is plastic, it's viscoplastic, but it's a solid viscoplastic material. And then I'm using terms of rheology. So this is the science of flow. So that's why I may have to go beyond the geotechnical engineers usually stay. So they are going to see something that not only deforms, but even can flow. So rheology is the science of the deformation flow. Rheology the word comes from the Greek. And if you do a translation, you see this is a flow science. That was something that was in geotechnical people's mind. So it's not something it's up to me. It's up to people that work with fluid dynamics, for example, or dambreak, or water dambreak. So that's people. The fluid dynamics would be guys who would be interested in this issue. No, because this issue, it relates to our material. So my tailings deposit. So I must understand something about fluid dynamics in order to understand how I can contribute in this new discussion thing that perpasses geotechnical border. So it's interesting, flow science, but there is a however here. Flow behavior of leaks, but it's also rheology talks about the deformation behavior of solids. So it's a science that try to connect the two words, the word of geotechnical engineers and the word of people that work with hydrology, with hydraulics. So that's why it took me some time, at least the last 2 years, I work on these issues of the hydraulics, but hydraulics not of water, but hydraulics of mud flow. There is something very interesting here. Let me just move again this guy here. O'Brien Julian has presented a paper in 1985 that is still important for us today because it presents a mud flow classification. The people that work with debris flow knows very well this reference. But this reference is also important for mud flow. And then we can see this mud flow classification. So it's very important to use the right terminology when you talk about mud flow. So let's start with something that's familiar for geotechnical engineers, landslide. So O'Brien Julian comes from maybe a field that is going to talk about a hydraulic thing. So it's moving things, so flowing things. So then we're going to talk about sediment concentration will be our variable in order to understand. It would be like more like a void ratio or even solids content. If you get material that's saturate, okay? So you can talk about concentration. Concentration expressed in weight. So it's over mass, mass over mass, or volume over volume. For geotechnicals, it would be more like mass over mass. And then to describe these different modes of flow, you have the flow characteristics. Let's begin with the landslide. What says about the flow characteristics? It says that will not flow. So that's very important thing. So it will not flow. Yes, that's the idea we have. Failure by block sliding. So it's like when you have that case of inclined plane and you have a block. The block has a weight. You can decompose this weight in two components. One is normal, the other is tangential. And this tangential thing is that the driving force of this block to slide, not to flow. We say slide, not to flow. And then you have, of course, friction that's going to be mobilized in order to prevent this to flow. But of course, depending on this inclination, you may have, of course, the slide, not really the flow in the material. We don't say flow in the material. So if you decrease a little bit the concentration, you may have a block sliding failure. So in that case was just something that maybe you don't see any deformation on the block. It's a rigid block sliding, running down the ramp. But now we can maybe have something that is going to part. And then we may have all the methods of analysis that we well known by the geotechnical engineers. So we use slope stability. So we need internal deformation during the slide. But even that, we can say that maybe it's a slow creep prior to failure. So you may see something before something happens, before you have something that is fast, large deformation. Then we cross this border between landslide, and then you have something that is going to flow. So flow is evident. It's a slow creep, sustained mud flow. There's a plastic deformation. There's something that is still cohesive, but very important, will not spread on level surface. It's more like the slump test. I think most of you know what I'm talking about. You can have a recipient where you put maybe fresh cement, and then when you raise this recipient, what we see, the material just slump. Okay, so on a level surface, this material just settle and spread a little bit, but does not spill away. Okay, so that would be a mud. You can say this is a mud flow, but you see the reach of this is very limited. So maybe you have centimeters in this case. In a scale that we're going to show you, maybe you have something like meters, tens of meters, no more like that. If you decrease the concentration, you may have a flow spreading on level surface. So you may see that something that goes a little bit further. Okay, but when you say further, maybe 100 centimeters, 200 centimeters, less than 1 kilometer, no more than that. Because, and even with that, you see there is a explanation here. When you go a little bit further, you see that the materials now, it's not, you cannot say that you have a mud flow, but you have a mud flood, because in this case, spreading is nearly complete on horizontal surface. So it's go far away, but not like water yet. You see liquid surface with two phases you have in this case. Oh, sorry, I'm here first. It says that spreads on horizontal surface, but maintains an inclined fluid surface. An inclined fluid surface means that you will have shear strength on this material. So this liquid. I forgot to say, in the other case, you may have like an angle of repose of this material once it stops running. And then you're going down to new borders with material that looks like almost like water. And then, of course, you have mud flood, and then something that resembles water. I'm sorry to take so long to explain this, but this is very important to classify your mud flow in order to understand the problem completely. So these is terms we're going to use in this presentation. So let's move to the case study. Our material, the material that I'm showing since the beginning of this presentation, is an iron ore fine tailings. So this is the grading particle size distribution. So if you consider here around the 200 mesh, this material, all of it passed this sieve, okay? And as far as fractions, we have like 73% of silt and 27% only of clay. Be careful here. When you say 27% of clay, so this is a product of the iron ore. So probably this clay fraction is not really clay minerals. So when you see the mineralogy of this, you see lots of other minerals that are not kaolinite, for example, that is a soil mineral. So you see magnetite, you goethite, you see hematite besides quartz. So that's why you see the plastic limit or the plasticity of this material is very low. So you are talking about something below 4%. And then when you consider the specific gravity, you see, oh, really, if you consider that most of the minerals has GS of 2.65, if you consider this stainless with 4.03, it's because, of course, the fraction that we are talking about, the clay fraction, probably is there is a contribution of hematite and goethite as well. So let's talk about the rheological tests. Yes. Before that, let me just, I forgot to talk about the shrinkage curve. So we perform also the shrinkage curve. So in this, the free shrinkage test is something very important to do, to understand how this material changes its consistent air, his loose water. So in this case, we start with a material close to the liquid limit and start to desiccate this material, allow this material to desiccate. And during this process, the material shrinks. We're going to talk about material, this fine material has some clay minerals as well. There's a shrinkage going on. So as material loses water, so this is in the abscess. Here is water losing water, water diminishing. And then we have the volume of material also shrinking. So when you plot the results, you see until get to this point, will be the contraction limit. The material behaves in a saturated state. So here is in a saturated state. Although it's desiccating, losing water, showing that crust maybe, the material is still saturated. The desaturation starts when it reaches the limit of contraction, the LC here. Okay, limit of contraction. So this is very important, the friction test to understand this change in consistency during the desiccation process. So the rheological test was performed using reconstituted samples. We'd love to have undisturbed samples, the ones that could be get on the field, in the field. But of course, our budget wasn't that big to do this kind of work. But we don't have any problem with that. We have done this before, and you're going to show you this is going to work. So we have these two kinds of samples. We test two kinds of samples. One we call disturbed, and this disturbed is the one that there is no fabric history. The one that I just set a goal as far as the solid concentration, and got there, just mixing water and solids. So there is no history, no fabric, no structure. So the grains are there, just mixing with solids and water, or any liquor that we have in the plant. So this is what we call disturbed sample. So we're going to talk samples with 60%, 75%, 8% solids content. But if you're saying that your work with disturbed, we get to that concentration without any fabric history. So any sedimentation, any consolidation, any desiccation. That's the difference with we call undisturbed samples. So the ones that have a history, have a fabrical history. So what we have done, we have this cup. On this cup, we place our sample. Let the sample this sedimentate, let the sample consolidate, and then let the sample desiccate. So that's why this this type of sample preparation resembles what happens in the field. So that's why you call this undisturbed samples. So the equipment is more something like you see here. It's a very modern rheometer. It does rotational and oscillatory testing. And the geometry, I have shown you before this cup where we place our sample. We're going to deform this material. We're using this geometry that is well known for geotechnical engineers. It's a vein, a miniature vein that's going to be introduced here. And then you're going to apply a torque. And then material is going to resist and deform. So it will be measured these quantities, and then we have the rheological results. So what will be the test that we performed with rheometer? We have of course, with the rotational tests, we got the main information, that is the flow curve. In order to get the flow curve, so we place that material and start rotating that vein in a certain shear rate. And then we measure the shear stresses. And there's two ways of doing this. One, controlling the shear stresses, or controlling the shear rate. So you can do both. You have done both, okay? We also perform tests to see the thixotropy behavior of this material, if it has or not has this kind of behavior. With the oscillatory testing, what we have done is completely different testing, because in this case of the rotational, we just start rotates the material. We don't stop rotates. Okay, that you have the angular deformation keeping growing all the time. In this one, the rotation be something like this. I'm going there and I'm going back. I'm going there, I'm going back. I'm going there, I'm going back. So it's oscillatory. And then you can fix, for example, the frequency of this oscillation. This is a dynamic test. And increase the amplitude of this. So the amplitude can be not only this, but maybe the next will be like this, maybe like this, and then amplitude is increasing. So be like this, increasing the amplitude, but of course back and forth. Okay, or you can maybe do a different way. You keep the amplitude, but change the frequency. And then they have this frequency sweep. So these tests are very important to discuss the gel-sol behavior. So if you remember the chemistry, gel behavior is more like the material behaves like more like a solid, and then here more like a liquid. Because our material in the tailings deposit probably is going to be in a gel state, you want to understand that if this material can be in a sol state or in a liquid state. So that you have to understand this in order to do a rationale on mud flow. Otherwise, you don't understand what you're doing. So that's why we invest a lot on rheological test types and understand which test can give you as far your application. The numerical simulations was done using Flow 3D software. Its last version. We try other softwares as well, but this one was the one that was nice for us as far as our understanding of the mud flow. You're going to see that this is something that you don't need to input a hydrograph of your reservoir in order to have the dambreak study. The material is going to the material that's going to be involved in the dambreak. The program itself is going to do this for you. So this Flow 3D, or the Flow 3D, is a very powerful software. Many other fields we use this software. In our case of mud flow study, we use this elastoplasticity model that they have there. Consider gravity non-inertial reference, and of course, a property of viscosity and turbulence. Okay. The simulation was for a hypothetical case, so we are just our point was just to look at the issue of changing the rheology, or talking about the deposit history. So that's why we're not considering a real case of a downstream valley case or a real reservoir. So we have a hypothetical TSF failure consideration, and a very simple one. And then the simulation time was of 420 seconds was enough for us. So this is the geometry of our model. You have divided in two parts. The first part, the reservoir. So the whole thing is a parallelepiped. So it's a three-dimensional geometry. But the first part was the reservoir that is this dimension, 100 meters in this direction, x direction, 1 meter in the y direction, and 10 meters in the z direction. So a volume of 1,000 cubic meters. The downstream valley was like this. At the beginning, we start with a 500 meters downstream valley in the x direction. In the model, we had some sections that we measure flow quantities like flow rates, like velocity, like submergence. So you have this for 50 meters, 100 meters, 200 meters, 500 meters, and so several sections where we have discrete data, output data. Of course, and start with level terrain. So it was very important thing that later we have a scenario where we change this. So these are the scenarios. We start with something that will be familiar for the hydraulic guys. So dambreak, when in the past, dambreak was just performed for water reservoir. So we start with this as a reference. Then we move for a tailings deposit that has a 60% solids content. Then one that was with a 75 solids content. The number 4 is the same as number 3, but a non-level terrain. So there's a downstream slope grade. So you see. The 51 was one that with 8% solids content. And the last one is the same material, but using a field rheological data. I have presented to you that small scale field test. Remember, with the 4 centimeters. So this former student has done measurements there And then we use the undrained shear strain that is in kPa, but for rheologists is the same as what we call yield stress. So for the rheology, you have the yield stress, it's the same idea. So here you have a PA scale. So when you try to, that vein, and the rheology try to make a torque on that vein, rotates that vein, it's going to shear that vein, and then you're going to measure what they call yield stress. So, but in the scale of PA, the continuation of this scale is what the geotechnical engineers call undrained shear strain. Okay. Unfortunately, I'm going to skip this. I apologize for that, because otherwise I'm not going to observe the time that was reserved for me for my presentation. So these are the rheological results, and I've just talked about the first one, where you have the 55% solids, and then is a flow curve. So here the shear rate increasing and the shear stresses increase as well. And then you have like this beginning of the test where the material just deform, okay? And then it's starting to have large deformation, and then maybe it's going to flow. And this here is very important. The flow curve, I can get the yield stress. You see the number here, 60 PA. This is for the undisturbed sample. For that disturbed sample was 17. So see the big difference here. In our case of dambreak analysis, we use this condition because that is the condition that really matters, because that's the condition of my material in the field, not this one that was produced in the lab, just mixing water with the solids and then get the rheological data. This is not correct to discuss. This is going to work only when you discuss the material that is flowing. Then, of course, all this structure, all this fabric is going to be destroyed. And then, of course, the rheological data will be the same for both in both cases. I agree with that. Unfortunately, I'm not going to show you this. I'm going to skip to the dambreak analysis. So this is, I'm really sad about that, but anyway, let's leave this. And then we're going to see the scenario of the dambreak analysis. As I said, we have 6 different scenarios. So we are going to show you a video. So at the beginning, I'm going to show just qualitative ideas, how this thing is going to happen. And so that's why I'm showing a video of each one of those scenarios. So the numerical simulation shown in the video. And then we're going to analyze quantitatively this later. So in the case of the water, we have this. Let's understand this is the, of course, this is the reservoir before fail. Here you have this scale of velocity. And then I'm going to start the show. Have you seen? So during the water flow, what we see that is a very fast process. So you're talking about a simulation. These are meters, it's not centimeters. Okay, that's why it takes a while for the wave propagation to happen, even with water. Okay, let's move it, show it again. But at the end of this simulation, you don't see anything, any material left. Or if you see, it's a very thin layer of material. The second case, is the scenario with the tailings at 6%. So let's see. So it's interesting to show that the material is still moving. In this case, it's going to move until it reaches like 730 meters before stop. So it starts here, and remember, this has a height of 10 meters and 1,000 cubic meters. And then the materials stop running at abscissa of 630 meters. So let's see the third one. 75%. You see it is moving, and then stop it. And in this case, in the previous one, we can classify that one as a mud flow. In this case, sorry, that one is a mud flood. We are talking about water floods, a mud flood. Now we have what we call a mud flow, according to that O'Brien classification. So in this case, we have a material that reaches a abscissa of 225 meters. So there is you see an angle of repose of this material. So it's very light ramp, but there is an angle of repose for this material. Of course, when this material is going to start desiccate or starting there, maybe you may have something angle of repose a little bit steeper than that. Let's move to the fourth case. The fourth case, remember, is the same as third case, but it's a non-level terrain. And this non-level terrain, it's very important to say, is 1.1 degree inclination, or if you want, 1.7 ramp, or less than 2%. So in that case, let's see what's going to happen. So the material moves like mud and stop running at abscissa of 630. Here, it seems that it stopped here because our simulation stopped at 420 seconds. But if we did a simulation, they allow a higher time, a longer time for the simulation, and then you see this material stopping at 630 meters. So it's the same as we got for the case number 2 with the tailings at 6%. So now we have a tailings at 75%, but it's a non-level terrain. So it's very important understanding this. So the next case is the one that has 8% solids content. So in this case, you see, stop it at a abscissa of 125 meters. So the spread wasn't that far, okay? So it's something that maybe is in the limits of mining property. So it's something that maybe is important to prevent to happen, but of course does not have the same consequences of the water flood or the mud flood. The last one is that my former student's case with the data. Oh, sorry about that. And then we see, we changed the scale here just to see what's going to happen. And then we have the landslide in this case, okay? So the material reached the distance of 20 meters, no more than that. So it stopped deforming, not flowing, or stop sliding at abscissa of 20 meters, okay? You see also the angle of repose very steeper than the other ones. So I'm coming to the end of this presentation, but before that, let's let's look at the quantitative of this, okay? And the quantitative of this, we have to look at the hydrograms. The hydrograms relate the flow rate on the ordinates with the time. Under this curves, if you consider the area, then you have the volume, okay? And the hydrograms is plotted for section 0, section 50, section 100, and section 200. It's interesting to know if you consider, for example, this hydrogram at 60, you see, depending on your case, in this first slide, we consider just the basic scenarios. The number 1, 2, and 3. Remember that number 1 is water. The second one is 60%. The third one is 75%. And in all this case, of course, the material passed the section 100 meters. But you see, there is a delay for this material with 70%, 75%. This delay is very important for considerations of safety. When you consider emergency plan action, EPAs, or evacuation of people. So this delay is very important, because if you are here at this abscess, if what would fail was this material at 75%, you may have some time, not in here, not that much, to do something, okay? So all countries have these regulations regarding what we did to know as far as this flood area that is going to happen with the result of the dam breaks. But anyway, you see, these are the hydrograms. Of course, the hydrograms related to water will be the ones that will be the higher, because of course this is material that flows very fast. So in this case, because flows very fast, the flow rate is being high. And then, of course, for the other materials, the flow rate is going to be a little bit lower. And then, of course, for 75 will be the one that's be the lowest. Remember, the velocity or the speed of this material is going to be much less than the other ones. For the complementary scenarios, one that is inclined, the one that is with 8%, and my former students, Pena, you have shown you in this case just for the abscissa equals to 0. We are talking about the foothill of the tailings wall or the tailings dam. It's interesting to note, because these hydrograms in this case, are going to show you, as I said, under this curve, you have the volume that passed through that section. If you consider that this is the flow rate in the time, at this time, there is no more material coming from the reservoir, okay? As far as the 75%, you can say that if I have integrate this area or get to this area, I have the volume that really was released during the dam break. So the same applies for the 8%, but here you see there's no more material leaving the reservoir around maybe 75 seconds. And my student says that after maybe 8 seconds, there is no more movement. So the landslide is really fast, but everything stops. So you have a static situation after 8 seconds. So another thing is very important is submergency. submergency is the amount of material or the height of the water level or the or the mud level that pass through, in this case, at several sections, at 0, 100, 200, and 500. Of course, in case you have because we are talking about basic scenarios, we are talking about water 60% and 75%. So in all these situations, especially in these three situations, that we have all materials passing through, okay, these sections. The first one is the submergence of 75%, and then this one is for 6, and this is for the water. Let's focus on the 100, abscissa 100 meters, and then we see there's a feature that is common to all of them. There's maybe a peak, and then in this case it has a plateau. Okay, this plateau. What does this peak means? First of all, let's pay attention to that delay. So at that point, we're going to see the material accumulates there, okay, and has a high elevation for this accumulation. And then you see, as the time goes by, you see there is no more change in the heights. It means that for this particular discharge of 75% tailings, and this section, this material is going to remain there. So like a 3 meter of material there. In this case, we don't have this plateau yet. So the material is there is going to still be less materials is going to remain there. And of course, in case of the water, this time is not enough for has 0 water in this section. The last picture that I'm going to share with you is this one. Is the released volume. The released volume after the TSF failure for scenario 2 was 81%. It means that, remember, it was you have like 1,000 cubic meters. So just remain there 190 cubic meters. So 81% was released. So was downstream valley. Does mean that went far away, because we have talked about this before. The material stopped at abscissa of 630 meters. In the scenario 3, the 75%, 57% of material was released. So less than almost half of the material is still there in the deposit. That situation where you have no level terrain, you see there's the material that was released was the same as the one that for a more diluted or less concentrated material, with 60%, here was 75%. The fifth scenario, the one that has 80%, you have a 42% of material that was released. And the last case with my students was just 90% of the material went beyond the foothill of the initial tailings deposit. So let's move to the conclusions. My conclusions are in three aspects of it. First of all, I think I hope I can convinced you that a good understanding of deposit formation is essential for any work that you try to do with the tailings deposits. If you're going to build something on tailings deposits, or if you're going to do a study like this of dambreak, so take a time, try to understand your deposit before you do something. As far as the dambreak analysis, without considering the positive fabric, you cannot evaluate correctly if material is going to deform or is going to flow. You have to see maybe the material is not going to move, or it's going to deform, but not to flow. This is especially the case of deposits from alternative disposal methods: subaerial, thickened, tailings, and paste. Remember, the material is going to be discharged maybe with a high sawdust content. And that thing is going to be higher and higher as the material desiccates. This research used the Flow 3D. It was interesting because the literature, when they talk about the break, usually you have a hydrograph. You have the input of the dambreak usually is a hydrograph. You have to provide your flow model with the material. There's the hydrograph is materials you're going to provide for the materials going to move. So Flow 3D allowed us not to have a hydrograph. So the material that moved was the material that was supposed to move because of these rheological properties, because that under strain, under shear strength. So that's why I think this apparently this Flow 3D has this capability. I don't know if other programs has this, but the commercial ones that we tried, we had to work with this hydrograph. In rheology, sorry, I'm going to skip this, but one thing that I'm going to mention, all these simulations was performed with, of course, with the undisturbed samples. This is very important for the beginning of the flow or the deformation. But of course, when the material is going to stop, in that case, it doesn't matter if you use one or the other, because I think in this case, you should use the disturbed rheological data. But the program, sometimes you cannot use different rheological data for the beginning of the movement and the end of the movement. I think you don't have a program, a software that you can choose this. So this is a suggestion for developers, software developers, to implement this also. It's very interesting to understand this solid viscoplastic behavior. You see, until you reach high shear stress, this material is not going to move or not going to flow. Maybe it's going to deform, like the geotechnical engineers. Geotechnical engineers work with the shear and the strain. Flow is shear stresses, and the shear rate. So it's a different word, but one is the continuation of the other, okay? The numerical simulations, let's see, rheological properties influence directly in the wave propagation characteristics and release material due to TSF failure. So it's very important to do properly this kind of investigation, okay? Non-level terrain, like in my country where we live in mountains terrain. So in our case, just 1 degree or less than 2% hemp makes something that was thick, looks like a less concentrate material as far as flow. Okay, so was one thing that was a mud flow, it behaves like a mud flood. Okay, using that classification. Minor deposits where discharge is discontinuous and material experience desiccation should follow specific regulation based on performance. That's a problem we have in Brazil, because in our dambreak analysis these days, they say that you must consider 100% of your reservoir volume involved in the flow process. And we have proved to you that in case of Daniel's case, it was just 9% or maybe 40%, but not 100%. Okay? So since in the case of failure, its spreading is limited and therefore do not present the same risk as conventional TSF. So that's something that the regulator has to understand and change the regulations. And also the society has to understand because the mining is going to change the way they produce their tailings. And people have to understand that what they have seen, Brumadinho in Fundão, is not going to happen anymore. Okay? I'd like to, before I finish, I'd like to do some acknowledgements. First of all, I'd like to say thank you to my former PhD advisor, Dr. Dobroslav Snidacic. He was the guy that introduced me on these issues of consolidation and desiccation. My PhD was on desiccation of soil. Most of the things that I present to you tonight is work done by my former students. I'd like to name it Ana Paula, Daviele, Francisco, Luciana, Daniel, Mariana, and especially Deborah, my last student, the icing on the cake. And to all of you for being so nice to spend your precious time with me tonight and stay with me to turn off the lights on this important symposium. Muchas gracias.
Thank you very much, Professor Waldyr. It's excellent exposition. We have one question. Eric said, what value of yield strength of solid concentration is required to consider dambreak analysis using FLO2D? It requires a dambreak analysis to modulate filtered tailings.
Yeah, we're talking about flow 3D, not flow 2D. Although
Flow
this
2D.
the analysis is like more a two-dimensional analysis. I agree with you, but of course the program, its name, it's flow 3D. If you understand your question, what the value of the yield strength or solid concentration is required to consider dambreak analysis, it's not the software, it's the material that's saying something to you. I tried during my presentation to classify the movement. My last student was something like was a landslide, in case number 6. In case number 5 was a mud flow. And of course, the input data I cannot show you, but the yield stress for the case of, or maybe the 5th case was like 5 kPa or so. In case of my students, the last one was a landslide, was like 40 kPa. And of course, for number 3 and number 2 was like less than 1 kPa.
Okay, it's one question, nothing more. Ingeniero Josepia, le cedo la palabra.
If you can speak in Spanish slowly, I can understand you as well. No problem.
Okay, thank you.
Estimado doctor Waldyr, realmente muchas gracias por aceptar ser ponente en este primer simposio internacional de ingeniería geotécnica de la ciudad de Oruro. Muchas gracias, profesor. Le invitamos de favor a despedirse del auditorio presente, de los participantes, estimado profesor.
I'd like to apologize for taking that much time that I was supposed to use just 40 minutes, and then I use more than that, and there is not much room for questions. But I'd like to thank you very much for this invitation. I had seen the programma, and I realized that very nice people was during this week. So you guys are really have a very nice symposium. Maybe the worst one was me at the end of this symposium. I apologize for that, being not the same level of my maybe previous colleagues, Dr. James before me tonight. So anyway, thank you very much. For me, it's the first time I've done a presentation in a different country in South America. So it's really first time. Maybe next time I'll be speaking Spanish.
Sí. Bueno, gracias, profesor. Bueno, pues para finalizar de mi parte, me gustaría agradecer a Geotecnia Brasil por la transmisión en vivo de esa red. También me gustaría finalmente agradecer al capítulo estudiantil ante la Sociedad Mexicana de Ingeniería Geotécnica de la Escuela Superior de Ingeniería y Arquitectura S.A. Zacatenco. También al capítulo estudiantil ante la SMIC de la UAM. Realmente muchas gracias por ayudarnos a que se realice este primer simposio internacional de ingeniería geotécnica. Esta es la primera actividad que estamos desarrollando y es el lanzamiento de esta nueva asociación. Como futuros proyectos tenemos un curso taller sobre Geoslop, quien nos dictará en el mes de noviembre la candidata doctora Maribel Trujillo del Instituto de Ingeniería de la UNAM. En el mes de diciembre tenemos el primer coloquio internacional sobre pruebas SPT, a la cual están cordialmente invitados. Muchas gracias. Para la clausura hemos invitado a un representante de la Sociedad de Ingenieros de Bolivia Departamental Oruro. Adelante, ingeniero Denis.
Muchas gracias. Un saludo muy cordial a Richard Josepia y a Sergei Bellot, miembros de la directiva de la Asociación de Ingenieros Geotecnistas de Oruro, como parte del Colegio de Ingenieros